Okay, let's continue from where we left off last class. Structure of metals. How do we know which metal is which? Well, we know that by observing its physical and mechanical properties. By knowing these properties, we can predict its behavior, and by knowing its behavior, we can predict its usefulness for whatever we're using it for. Could be dental technology, could be manufacturing of some type of machinery. So we need to know how hard the metal is, how bendable the metal is, so that we can predict how useful it will be to make that specific restoration or product. Now let's go into the physical properties first, and then we'll go into the mechanical properties. The physical properties are the inherent characteristics and items or physical properties that can be measured. Now these properties cannot be changed. It is inherent in the material, in its elemental structure, its crystalline structure, which also makes its physical properties be what they are. These are listed on the manufacturer's packaging. The alloys are listed in what it is they are made out of, like all the elemental structure of the alloy. Let's say it contains elemental gold, palladium, silver, rubidium. These are the makeup of the alloy, and all these are listed in the manufacturer packaging according to how much of each it contains. Mechanical properties are the properties on how the metal performs. There are laboratories that test the properties of the mechanical properties of the metals. They have machinery that tests the hardness, the softness, the ductility, transparency, things like that. These are sometimes listed on the manufacturer packaging and sometimes they are not. The strength generally is listed because when we are using it for restorations, we need to know how malleable, how ductile, and how strong the material is. Mechanical properties of metals. The first we're going to go over is the hardness, which is the resistance to scratching or indentation. This is basically the way the material is resistant to, like, let's say if you are scratching it with a knife, or you're scratching, like, let's say a glass and you're writing something on it with a diamond. The harder material always scratches the softer material. Normally, the harder a material is, the less malleable it is. Malleability we'll go over later. And these are tested by different tests. The hardness tests are as follows. The Vickers hardness test is a hardness test based on the shape of the testing machinery. So this is a little video on how they test for
the Vickers hardness test. The hardness of a compressor wheel for a turbocharger is to be measured using the Vickers method. The main principle of this hardness testing method is to press a pyramid-shaped diamond indenter with an exactly defined force onto the test piece and then to evaluate the surface area of the indentation. First, the tester has to prepare his testing machine. He takes the Vickers indenter with the four-sided pyramid and inserts it into the mounting device of the testing machine.
So that's called the indenter. So if you notice, there's a specific shape to it.
He then places the compressor wheel on the support table and rotates the microscope lens into its working position. With a hand wheel, he adjusts the height of the support table until the test piece surface is displayed in focus on the screen. Next, he moves the test piece around on the support table until the right spot for the hardness test is displayed. Now that everything has been prepared, let's begin with the test. After pushing the start button, the diamond pyramid pans down and carefully touches the test piece surface. The test force slowly increases to its specified value. After holding the test force constant for a certain time, the indenter lifts again, pans back, and the microscope lens resumes its former position. This is the magnified indentation on the display screen. With the control knob, the tester now places 4 measuring lines at the corners of the indentation. Doing that, he can easily measure the length of the 2 diagonals. Finally, he only has to push the input key. The Vickers hardness value will then be calculated automatically. It is equal to the test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The Vickers hardness of our compressor wheel is displayed on the bottom left-hand corner of the screen and amounts to 125.
As we can see, the Vickers hardness is tested with a diamond-shaped tip. So that's what really determines the different hardness tests, the shape of the indenter tips. The formulas we don't really have to worry about, but I expect you to know the shapes of each hardness test. This is the Brinell hardness test, and please observe the shape of the indenter.
The Brinell hardness test. Using the Brinell method, the hardness of a turbocharger housing is to be measured. First of all, the tester has to make himself familiar with the testing machine. A monitor and the control panel are positioned in the upper part of the machine. These are used to select and program different testing methods. Below the control panel, a microscope lens with a digital camera and an indenter are installed. These 2 elements are connected to each other and rotate towards the test piece as required. It is also possible to select and exchange the indenter, so different methods of hardness testing can be conducted on the same testing machine. The support table can be adjusted in height, so the test piece can be positioned at the correct distance to the microscope lens and the indenter. After becoming familiar with the machine, let's start the experiment. The principle of the Brinell hardness test is to press a hard spherical indenter with an exactly defined force onto the test piece, then evaluate the surface area of the indentation. The tester selects a suitable spherical indenter and inserts it into the holding device of the testing machine. Next, he puts the turbocharger housing onto the support table, rotates the microscope lens into vertical position and adjusts the correct height of the test piece. After bringing the test piece surface into focus, he selects the exact spot where the hardness test is to be made. By pushing the start button, the hardness test procedure begins. The testing machine rotates the lens back to its resting position and places the spherical indenter carefully on the test piece surface. Gradually and shock-free, the test force rises to its specified value. After maintaining the test force for a certain time, the indenter automatically lifts off again and the microscope lens pans back to its former position. The indentation can now clearly be seen on the monitor. With the control knob, the tester places 4 measuring lines on the edges of the indentation to measure its diameter. That's it! The testing machine can now calculate the Brinell hardness. The hardness value is defined as test force F in the old unit kilopond divided by the area of the indentation A in square millimeters. The result is displayed on the bottom left-hand corner of the screen and amounts to 250.
Next is the Rockwell hardness test.
The Rockwell hardness test, scale C. In this video we will show how the Rockwell hardness test works using a gear wheel. The basic idea of this test method is to measure the permanent depth of indentation of a hard indenter under a test force. In the process variant scale C, a rounded cone made of diamond is used as an indenter. In step 1, the diamond cone is pressed onto the test piece surface with a minor force of 10 kilopons. The depth of indentation under this preliminary load is the reference point. In step 2, the test force is increased by 140 kilopons, which is acting as the major force. This means that an overall force of 150 kilopons is now acting on the indenter, and this force is held for a certain time. In step 3, the major force is removed again. While the minor force is still acting, the permanent increase in depth of indentation E is measured. This is how the Rockwell hardness is calculated. Rockwell hardness HRC is equal to 0.2 minus permanent depth of indentation E in millimeters times 500. Let's take a look at how the test is carried out in practice. The tester selects the conical diamond indenter and installs it in the testing machine.
So this one is a little cone.
Then he picks up the gear wheel and puts it on the support table. After rotating the microscope lens to its vertical position, he can adjust his test piece. As soon as a focused image can be seen on the screen, the surface of the test piece is in the correct height. The test can start. In modern testing machines, the Rockwell hardness test is fully automated. That's why the Rockwell hardness test is used so often in automated production lines. That's it! The Rockwell hardness of our gear wheel is 55 HRC. This result is displayed on the screen.
HRC is basically short for the Rockwell hardness test. The next one is the Knoop hardness. Now this is another shape there, and the Knoop hardness is tested using a stretched diamond shape, and this is more of a scratch test. So they use this mainly on glass materials, or materials that need to be extremely hard. So as we see on the left side, you see how the glass breaks apart a little bit as the scratch is being applied, and the right side stays more of a line. And of course that's Corning Gorilla Glass, is the glass that's used on most phones. Fatigue strength. It's the ability of a material to withstand repeated stress. Like when you put stress on a spring or something like that, that's fatigue strength.
Many everyday items are not loaded uniformly, but rather non-uniformly with periodically changing loads. This is quite obvious in off-road biking. Frames, handlebars and wheels are subjected to high alternating mechanical loads. It is just as obvious in the case of a garage door spring. The spring is unloaded when opening the door and loaded when closing the door. The connection rods of this old compressor have endured a large number of rapidly changing tensile and compressive forces. Even when cycling quite moderately in the city, many components are exposed to periodically varying loads without us being aware of it. The crank arms are alternately under load, then swing back almost load-free, are under load again with the rhythm of pedaling. The spokes, the pedals, even the individual links in the chain are stressed periodically. Aircraft experience quite different stresses during take-off and in turbulence than on ground. This type of loading is generally termed fatigue loading, and the material responds to it fatigue. The term fatigue is used because it takes some time for the failure to occur under repeated loads. The problem with materials is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had borne the opening and closing of the garage door about 60,000 times before it finally fractured. The broken exercise equipment, a torn blade of a fan, a bandsaw blade full of cracks, the broken screw, a defective universal joint, and many other examples show how important this phenomenon is.
Okay, so that's fatigue strength. Ductility is the ability of the metal to be pulled apart and then made into like a wire. This kind of stress is a tensile stress, meaning pulling apart. So ductility is the property of a metal that permits it to be drawn into thin wire. And this is particularly true of copper. We of course use a lot of copper wire in our electronics, and this is how it's made. It's basically pulled from a bigger chunk of copper and drawn through a little hole, and then it's drawn into a wire. So the ductility decreases as hardness increases. When you have a harder material, you can't pull it apart without breaking very long. So, and it's the opposite is also true. As ductility increases, the hardness decreases. So, as you can pull it apart very easily without breaking a metal, the hardness also decreases, so that metal will bend very easily.
Imagine you take copper metal and stretch it into a thin piece of wire. Would you believe that the copper metal would resist breaking while being stretched? This is a great example of ductility. Ductility, by definition, is a material that can be stretched thin when tensile stress is applied. It is the way to describe a physical property of any material. Although very similar, be careful not to confuse ductility with malleability. Malleability is a material that can bend or change shape using compressive force rather than tensile stress. Think of compressive force as the act of squeezing or pushing down on a material to change its shape. Some materials can be both ductile and malleable, or ductile or malleable only. Tensile stress refers to a type of stress that changes the length of an object in the exact same direction as the force being applied. Using diagram 1 as a guide, think of tensile stress this way. You grab that piece of copper metal and begin pulling it with your pliers. The copper metal is experiencing stress because you are pulling it, lengthening the metal until it is stretched into a thin copper wire. Your action of pulling is the force that is being applied. Just keep in mind that tensile stress can contribute to the ability of a material such as metal to stretch into a thin wire. Do you know the term for a material that is considered to be the opposite of a ductile material? This term is referred to as a brittle material. Brittle materials are quite different from ductile materials. Instead of stretching and lengthening, brittle materials can break when experiencing too much tensile stress.
So just as to recap, these are the hardness tests, and these are the shapes that are conducted with the hardness tests. You have the brittle with the rounded shape. We have the Rockwell with a thin diamond shape, with a cone shape, I mean. So we have the Vickers hardness, it's a square diamond, and we have the Knoop hardness, which is a stretch diamond shape. This is a recap of the properties of the metals, the way the force is being applied. So we have the tensile force pulling apart, we have the compressive force pushing together, and we have tensile force. So the idea of this diagram is that if we have a flaw in a material, it's going to break right by the flaw. And this is especially important in dental technology because of the functions of teeth. If we have a crack in one of our bridges, the compressive strength can break that bridge right at the flaw. If we put a tensile stress, obviously right at the flaw it's going to break, and depending on the shape of the flaw, it creates a different kind of a fracture. Some flaws may create a fracture that fractures right away, and some flaws may create a fracture that fractures over a longer period of time. When we compare the different materials, the different metals here, we have copper, silver, platinum, copper, aluminum, nickel, cobalt, and these are the different metals showing how ductile they are or how resistant they are to tensile stresses. So we have a low ductility on the right, and low ductility means it's a harder metal, but it's also a metal that will break easier. Medium ductility, obviously, it has a less ability to withstand the tensile stresses, and high ductility is gold, silver. These are softer metals that we can actually draw them into wires in different shapes. The next property is malleability. Now, as we heard before in the video, malleability is the capability of the metal to change shape under compressive force or under blows of a hammer. You can hammer them into thin sheets without the metal crumbling. It's just going to change shape. This helps in fabricating gold crowns because we're able to burnish the margins and close them with with stones and things like that, because the stones kind of have little particles that actually hammer the material into shape. So if we have a stone that's not very abrasive and we put it on the margin with the quick spinning burr, it will actually shape the margin in so that we can close the space. This is more true with gold than with non-precious alloys. Non-precious alloys are not very malleable, so it's a lot more difficult to burnish them. Gold is the most malleable, so obviously we see here, and I just told you guys, it's very easy to close the margin on gold crowns. Density is another property. There's a physical property, high specific gravity. Okay, high specific gravity means high weight or high volume. This is where the atoms are very close together and they have a higher atomic weight, so the whole metal becomes a much heavier metal. So it also means that when you compare it to water, it's heavier. So if water is 1, let's say a dental alloy is 13, so you have 13 times the mass of water. And this can be calculated, by taking the specific gravity of wax to, by the specific gravity of the density, and we can get the weight or volume of that specific material. If we wax a crown and we multiply the specific gravity of the metal measured in the same grams or pennyweights, then we get the weight and volume. So we measure the wax in grams, then we take the specific gravity in grams per centimeter cubed, and by multiplying the two, we get the weight of the metal needed to replace that volume that the wax leaves behind after burnout. Melting points and boiling points. These are important, especially when we are soldering gold bridges and things like that. The melting point of solder must be lower than the melting point of the bridge that we made the metal that we made the bridge out of. Because if the solder melts too close to the melting point of the bridge, we're going to melt the bridge. So we need the solder to melt before the metal that is composing the bridge. This is the comparative malleability of different metals. Now, as we see here, between the ductility and malleability, we have the high malleability here of the gold, silver, copper, tin, and platinum, but we can also see that lead now is transferred over to the high malleability. So even though lead has a medium ductility, it has a high malleability. So it can be ductile to a degree, but it has a higher malleability because it's easier to deform under compression. Low malleability metals are chromium, manganese, antimony, and bismuth. And these, since they are low malleability metals, they will break easier. Specific gravity and density. Specific gravity is the weight of the unit of metal as compared with an equal volume of water at the same temperature. It's important that we have them at the same temperature because metals expand and contract with changes in temperature, and so does water. Specific gravity is a factor in planning and design of any cast restoration. We use it to determine how much metal we need to use in our casting. Different alloys will require different amounts of metal, and because they have different specific gravities. These metals have a composition of different elements, so they all need to have a determined specific gravity, which is measured by the company that manufactures them. The specific gravity of water is 1. So water is used as a base number to calculate the amount of metal we need to use in a casting. So they assigned water a specific gravity of 1 because water is what we compare all other elements or compounds to. So if we have a specific gravity, for instance, of a metal, let's say a ceramic metal, which has a 13.5 specific gravity, that means that particular metal is 13.5 times heavier than water. If we have a metal that is a specific gravity of 2, that metal or that compound will be twice as heavy as water if you use the same volume. Let's say if you put 1 milligram of water is 1 at a certain amount, like a centimeter cubed as volume, then a centimeter cube of that particular metal is going to be 13.5. So the volumes are the same, the weights will be different. Chemical properties of metals. Metals can form alloys with other metals, and they can combine with other elements as well. Metals react with various materials depending on their atomic structure and depending on the reactivity of that particular metal. For example, let's take iron. If we have iron, and iron can easily combine with oxygen, so that is called iron oxide, which is corrosion, which is also called rust. Second metal here is magnesium. We add a lot of heat to magnesium and it will start reacting with oxygen. So magnesium starts burning. It's actually a metal that burns. This metal burns extremely hot and it's very difficult to put out. So they have, as we went before, we went over fire extinguishers, and that was in the non-metallic class. There's a specific fire extinguisher to extinguish magnesium fires. So that is super hot. And a lot of these reactions with the metals, they have an exothermic reaction, which means it puts out heat. Among these metals are on the left side of the periodic table, which is sodium, lithium, potassium, radium, and we have other metals like cesium, which we don't use in dentistry, and we have francium, which are the most reactive metals, but some of them don't last long. Like francium, for instance, only can exist for about 20 minutes in nature, so it's very difficult to observe because that actually has to be manufactured by a special process. Cesium is super reactive. It almost explodes when it comes in contact with water. Sodium also has an exothermic reaction among lithium, potassium, and radium. These are very reactive metals that we don't normally see in nature because they react quickly with other materials and they dissipate. Some metals are less reactive. These are the ones that we use in dentistry: gold, platinum, silver, and palladium. These four metals are in the noble class of metals, and they are not very reactive, which means their outermost electrons, valence electrons, The shells are almost full, so it does not react with other compounds very easily. Base metals in dentistry. So base metals are basically substitutes for gold. They are non-noble metals, and some of them, like chromium, is not very reactive but somewhat reactive, and it doesn't oxidize too much because of a property called passivation. Passivation is forms a light oxide on the surface of that particular metal, and it prevents oxygen from getting to the surface of the metal, thus not oxidizing very quickly. So that metal is chromium, and we frequently use it in the base alloys in dentistry to prevent oxidation or slow down oxidation of specific alloys. Common dental base metal alloys are chromium, like I said, has the property of passivation. Cobalt and nickel are the largest constituents of most dental base alloys. Stainless steel is a carbon iron alloy that also has different metals or different elemental metals in there to prevent oxidation. Titanium is a hard, light alloy that we tend to use for dental implants, and sometimes they use it for airplane parts. It's very difficult to cast too, so it's very rare that we use it for ceramic work because it's very difficult to bond porcelain to special porcelains. Have to be manufactured to bond to titanium, and to bake these porcelains you need to have a nitrogen-based atmosphere to prevent oxidation during heating. And it's the same with casting titanium. It's an extremely difficult process that requires expensive equipment, thus very, very few labs could afford to have casting machines for this metal. So mostly titanium these days are milled, and they don't mill porcelain fused to metal frameworks because they, like I said, it's very difficult for ceramics to bond to. So titanium is very, very resistant to corrosion, and it's non-reactive almost when it comes in contact with tissues. So that's why they use it in implants, because the tissue is not afraid of it and it actually bonds to it. So when they put the titanium implants into the bone actually adheres to the titanium. These are the minimum fundamental characteristics that we need to be able to use an alloy in the mouth. First, it should not produce any harmful toxicological reactions. So, in other words, it should not produce any allergies. Some patients may be allergic to nickel or beryllium or things like that, and those types of metals, if they're used, they need to let the doctor know so that they can check to make sure that the patient's not allergic. It should provide an adequate resistance to corrosion and physical damage when in the oral fluids. So it should not tarnish or oxidize when it comes in contact with saliva. Physical and mechanical properties have to meet the minimum requirements depending on what we're fabricating. For instance, if we're making a bridge, we have to make sure that this metal is strong enough but not too brittle. So these metals have to have enough strength, and we have to know the hardness of these metals in order to use it in the mouth. We also have to make sure that during heating it produces as little oxides as possible. Although for porcelain fused to metal we may need some oxide, because some oxide promotes the bond of porcelain to the metal. We have to know properties like coefficient of thermal expansion, so that we can actually match it up with the porcelain. Mismatching coefficients of thermal expansion will crack the porcelain during firing. Technical expertise. Now, technical expertise just means how hard it is for an average technician to use the material. So we need to make sure that the metal is adequate business-wise. It doesn't cost too much in order to put it to use, and also it has to be easy enough to work with the average technician so that the lab doesn't lose money in fabrication process by losing hours. Sometimes if a material is too difficult to use, the laboratory is going to lose money because it's going to take longer to fabricate a prosthesis than it would with a different type of material. Companion materials like solders need to be available, easily, so that you can join the materials together in case things don't fit, or in case things happen, like you put a hole in it by mistake. You should be able to solder the metal instead of having to remake the entire restoration, especially if it's a very large involved restoration. These companion materials should be relatively inexpensive. These are the advantages and disadvantages of base metals. First, let's go with the advantages. They are stiffer, they are harder, so they are very strong. Sometimes, even though they are a little more reactive than noble alloys, it makes sense to choose a base metal for your restoration, because maybe you have a very long bridge that base metals would have the strength so that the bridge doesn't break. Like I said, long span bridges needs more strength in the material. The oxide, I said before, it enhances porcelain bond, but not if it's too much oxides. Too much oxides will hinder the porcelain bond because it creates a space between the metal and the porcelain. Base metals can be acid etched because of its grain structure. They don't have a smooth grain structure, so when you etch it, the surface becomes rough so that the cement can adhere more readily to it. And of course, let's not forget its low cost, which is excellent for the patients who cannot afford expensive restorations. Disadvantages: specialized casting techniques. This is especially for titanium. Titanium is super hard to cast. The regular base metals are not as difficult, but still it takes a little bit more finesse to cast them because of the way they melt. They don't melt like gold into like a very shiny ball. they have a crust on them, so you have to be able to tell when the metal is perfectly molten, so you don't overheat it and create excessive oxides, and you don't underheat it and not have it be able to flow enough. And obviously they oxidize easily, so you have to know how to oxidize these metals. High-speed grinders, they're very hard, so obviously you can't use low-speed grinders because it's not going to do anything. If you use steel burrs on these, the steel burrs are just going to get dull in a few seconds and it won't grind much. You're going to be wasting time. With this kind of materials, you're better off using the more expensive carbide burrs and with a faster speed in order to achieve a faster contouring. Like I said, it may over-oxidize and ruin the bond, so you have to pay attention to how long you keep it in the oven to oxidize it before you place the porcelain. May be allergenic, we went over that before. Many people are allergic to different things like nickel and beryllium and things like that, so we have to be aware of that. They may be carcinogenic, so because of that, many companies took out the beryllium and the nickel out of those metals because of these controversies. Beryllium is suspect, so it's been removed from many alloys. Alloys. Okay, what are alloys? Alloys are a mixture of various metals. So we make alloys in order to amplify the good characteristics of a metal and subdue the undesirable characteristic. So like let's say we need a hard alloy that doesn't oxidize that readily. So somebody might decide to mix gold with palladium. Palladium is harder with a higher melting range. Gold is softer, but it has lower oxidation rate. So if you mix the two together, you're going to end up with a metal that is harder than gold, but it oxidizes less than palladium. So this would be a gold-palladium alloy. Most metals in dentistry are alloys. The only alloy that we use in dentistry that is not an alloy, should I say, the only metal in dentistry that is used in its purer form is gold, and that particular gold is used to fill very tiny fillings because it is so soft that it would not be able to withstand the biting forces. So because it's so soft, they're able to pack it into the little cavities in the different bits and fissures where they may want to use it because they don't want to take too much tooth structure away. In dental alloys, there are as many as 9 or more different types of alloys depending on the properties the manufacturer is looking for. The following are the few metals used in pure form. Gallium was tried as an alternative to amalgam so that they wouldn't have to use mercury. Both gallium and mercury are metals that are liquid in room temperature. Pure gold, like I said before, you use it for small fillings. Titanium, we're using it on attachments, bars, implants, abutments, implant screws, etc. Endodontic silver points, these are little points that are made out of pure silver, and they used to use it in RCT, root canal therapy. They stopped using it really because it could not conform to those very fine dental canals. Metal alloys in dentistry. Titanium, they like to use titanium because it's biocompatible. Like I said, it doesn't react with many things, and tissues seem to like it. So it gets attached to bone very easily, especially if the surface is prepared correctly. And they heal into the bone so well that most of them can be used for the rest of a patient's life. We use it on implant prosthetic devices. Titanium is generally milled, it's not cast. So we would design the implant or restoration in a computer and then send it to the mill. We put in a block of titanium into the mill. The mill will actually carve the block of titanium into the restoration or implant that you need. It's no longer used for porcelain fused to metal, or if it's used, it's extremely rare. I haven't heard of anyone using it. The last time I saw somebody use titanium was in a laboratory about 25 years ago, where I went to visit. Filling materials. Most common, amalgam. It's between 67 and 74% silver, and we have tin, copper, zinc, mercury, and they're all mixed together chemically, and it forms a new alloy that is not as dangerous as mercury would be by itself. High purity gold, again, this is for filling pits and small cavities. Also with high purity gold, we can use it on inlays, but those golds are high gold content, but they still have other materials, so it would really be called a gold alloy. Soldering alloys, orthodontic alloys, these are like stainless steel wrought wire, so they have a specific flexibility for using it in orthodontics. Its composition is chromium, nickel, carbon, and iron. So these metals, this alloy does not rust very easily, and it can be bent, and it's very springy, so it's ideal for orthodontic retainers and moving teeth, things like that. And then we have the ceramic alloys, which we use a lot for post and cores, full crowns, and ceramic substructures. Alloys, these are the different types of alloys. We have the solid solution alloy. These are mixtures of metals that the atoms of different metals occupy in random positions in a crystal structure. As we noted before, metals are crystals. So in a solid solution alloy, these crystals have the atoms randomly structured, so it's not in a specific crystalline structure. They cannot be separated by physical means. In other words, you need a chemical process in order to separate the alloys from each other. These are brass, bronze, and sterling silver. These alloys are mixed together and they stay mixed together permanently. It's very difficult to separate them. We have eutectic alloys. These atoms mix together in liquid phase, but they separate in a solid phase. So if you look at it under the microscope, you're going to see the separate metal crystals and not a crystal that is made up of both metals. They will completely change from solid to liquid at the same temperature. Sometimes the solid solution, one piece may melt before the other. Eutectic alloys are used for dental solders because they flow very easily because they mix together in the liquid phase. They melt and freeze at a particular temperature that is smaller than the melting points of the individual constituents. So if you have two metals that make up this solder metal, one metal will melt at one temperature, the other one will melt at a different temperature. But if you put these two metals together, they melt at a lower temperature. Intermetallic compounds. These, the metal atoms will occupy a specific position in the crystal structure. So the crystal structure of these compounds, they are in a very specific place and they're always the same. As soon as it solidifies, as soon as this metal solidifies, it will always look the same when you look at the, under magnification, you look at the crystals. They're hard but not very ductile, and they're very brittle metals. So these are not very good metals to use for dental restorations. Intermetallics, as the name specifies, have the characteristics of both metals and ceramics. And as you remember, ceramics are fragile, they're brittle. So they have a little bit of this and a little bit of that. This is what a eutectic mixture is. And these are the little grains that are in there. They're generally brittle, easily melted, and subject to tarnish and corrosion. Used primarily in solders. Okay, so, and these metals, like I said before, they flow very easily, which is what we're looking for in a solder, because it has to flow right in between the little gaps that we need to join together. This is the comparative malleability of the selected metals, or the softness. So remember, malleability is a property of the metal that it deforms under compressive pressure. So if you squish it together or you hit it with a hammer, it will change shape. They're very soft metals. Medium malleability are the zinc, iron, nickel, cobalt, and molybdenum. And then the low malleability metals are chromium, manganese, antimony, and bismuth. So these are the high malleability metals, and gold is among them, which is why we have to make gold into an alloy in order to use them for crown and bridge. Where do we find metals? That's a question. Metals generally come from metal ores. Minerals that naturally occur in rocks that contain the metals or metal compounds in sufficient amounts to make it worthwhile extracting them. Now, most times there's very little metal in metal ore. So let's say you want to get an ounce of gold, you'd probably have to gather maybe 10,000 pounds of rock in order to be able to get an ounce of gold out of it, depending on how much metal is in that particular ore. That's why it's important to do tests on these ores where you found them and see how much gold there's actually in that area. Otherwise, it may not be worth excavating the gold ore because you'd be getting less gold out of it than you would have to put into it to dig it out. Metal ores are generally oxides, sulfide silicates, or native metals. The native metals are metals that you can almost see it in the rock when you look at it. It's kind of embedded into the rock and it's easier to cultivate. Extraction. It depends on the reactivity. Very reactive metals, heat, electricity, and metal. So extraction. How do we extract the metals? Well, that depends on the metal's reactivity. So if we have a very reactive metal, we would use heat and electricity, and that's what would get us the metal. In this case, it's sodium. So heat plus electricity equals the metal, sodium. Sodium is a very reactive metal. Reactive metals, you put heat and carbon. In this case, we get iron, Fe. Iron is pretty reactive because it joins easily with oxygen, forming iron oxide. So if you take iron ore and you add heat and carbon, you get the iron metal. Non-reactive metals, you basically heat the ore to a high temperature and just collect the metal. They have other ways of doing it, different ways of heating it, and that will allow you to extract the gold. These are some examples of gold ores. This is how it usually come. They take a little sample, then they put on a description, the sample, the weight, and then they'll try to extract some gold out of it and see how much they can get. This is another type of gold ore. As we can see, this is like reddish brown. This comes from the Carlin mine, and they mention gold ore. Here they tell you the amount of gold they could extract from this. So this is 0.116 ounces. So it's not a, it's like just a little over 1/10 of an ounce, and you need a ton, which is 1,000 pounds, in order to get 1/10 of an ounce of gold out of it. Now this is a very nice gold ore. You can see the gold inside. Now this yields a lot of gold, so if you have a property that has this kind of ore on there, you're very lucky because you're going to get a lot of gold out of this. So this is basically a machine that sifts the gold out of the ground. So they will take the gold and
today we're going to be running some high-grade gold ore that a customer sent up. We got about 300 pounds there, and we're going to run it through our turnkey system with the hopper and jaw crusher discharge conveyor into the hopper, and another conveyor up into the hammer mill, and then onto our 4x8 shaker table.
It's ground, so it's kind of mixed up with some water, and it goes into a big giant tray. Okay, and this vibrates, and as it vibrates it leaves behind the gold. Sifts through again, this brings it up, and it separates all the different particles that have different weights. And this is the residue that it comes out.
Almost all the gold ends up coming out of the top 3 grooves here. There's a little spilling over into the next couple of grooves, and that'll end up coming up out this groove right here. Now we've stopped everything so that we can see the gold and the separation with the other lower specific gravity materials. We've got some real silvery material in there, we're not sure what it is. The gray stuff is probably pyrrhotite. And most of the gold comes out of the top groove. Come across the table. And it just makes a real nice line of gold right down under the water bars. And into the trough, number 1 and number 2 high-grade quartz. Now when we're done running a couple 200 or 300 pounds, we've got to brush down the table because the gold hangs in the grooves, and we'd be here all afternoon to get it. So we brush it down, and this is really where we get our strong line of gold. The good part of this is just smoke on the table. The big pieces have come down already. They're already down here. These are the bigger pieces from the ore. And then on up here, this is actually fairly coarse here as well. And then we get up here, and this is just very fine smoke. Call it micron gold, call it flour gold. When we screen this, a good part of this will go through a 325 mesh screen.
We're taking the gold we recovered off the table and we're going to screen it into 3 different size fractions. This is the 100 mesh screen. Yeah, it's a little bit hard to see in the glare, but there's the gold on top of a 100 mesh screen. And there's the gold that went through a 100 mesh screen.
Now this is all the material that went through a 325 mesh screen. And we've got it fanned out pretty well, but you can see how fine it is. So there's that 325 minus. Now we're taking this 325 mesh video through a little loop, and I think that must be maybe 8 or 10 power. And you can just see the edge of it there a little bit.
Here are the results of our screen test. On the left is our 100 mesh plus. Next to that is 100 to 200, then 200 to 325, and here on the far right is our 325 minus. So you can see the variation in gold size the table captures, and there's a little bit more than an ounce of gold here. So the table did a great job.
So this is a pretty good result from 300 pounds of ore. Okay, so we come to the end of the presentation. Next class we're going to go over how do we get the metals out of the ore, and all different ways of mining for ore and taking the metal out of it, and not just as far as gold alloys but in general. So till next time.